Good morning. All right, we're going to look at exponential functions today, which is a different topic than anything that we've seen so far in this course. And let me define it and I'll explain why I say it's so different. Okay, so an exponential function looks like this. You have f of x equals a to the x power. All right, and so what is different about this? Well, notice that your variable, my x, is an exponent, right? So with polynomials we've had stuff like this. So here's an example of a polynomial. We've had g of x equals something like 3x to the fourth minus x squared plus 1. Notice that your variables are raised to powers, but the variables are not exponents themselves. Now with exponentials, we might have something like this. So here's an exponential function. Let's call it h of x, maybe 2 to the x minus 3 power, something like that. Right, so now the variables are in the exponents. And so we're going to have to learn some new techniques to work with exponential functions because, well, our normal algebra techniques to solve polynomial equations or linear equations won't work here. I can't add I can't add a 3 to both sides, for example, in this h of x to get rid of the 3 in the exponent. Okay, so what we're going to do first of all is kind of just look to see what these things look like, and I'm going to use desmos.com to show you what the graphs of exponential functions look like. Let's get an idea though with a table first of all. Okay, so I'm going to pick, here's x, and I'm going to pick two different exponential functions. The first one's going to be 2 to the x. So we're going to pick some values of x and just see how 2 to the x works. And then I'm going to also do 1/2 to the x power. So we're going to have, I should mention this value a is what's called the base. So the base is the a value. So here I'm going to show you if you have a base greater than 1, what happens, and if you have a base less than 1, what happens. And another thing we need to mention is that a is always greater than 0. All right, so we don't really consider negative bases or 0 as a base with these exponential functions. All right, so now let's pick some values of x and just see what happens. So if I pick 1, for example, then 2 to the x power, it means 2 to the first power. 2 to the first power. See, this would be 2 to the first power, which is just 2, not a big deal. And if I picked, I don't know, how about x to be 2? Then when I plug it in, what do I have? I have 2 squared. Okay, I can handle 2 squared. 2 squared is 4. Okay, and then you just keep going in this pattern. So if x is 3, notice I get 2 cubed, which is 8. And so notice as x is growing linearly, like x is just growing by 1 each time, my 2 to the x power function is doing what? It's multiplying by 2. It's doubling each time. Okay, so these things grow really fast. For example, at 4, I'm already at 16 in my exponential, okay? Now, a couple of things we want to point out. If I plug in 0, I get 2 to the 0, and 2 to the 0 is 1. All right, and I wrote it in yellow because that'll stay constant regardless of the base, right? And let's do a couple more. Let's extend my table down. Let's pick, how about -1? Well, then that means I have 2 to the -1 power. And remember how negatives work? A negative power means reciprocal, so that's actually only 1/2. And -2 would be 2 to the -2 power, which is going to be 1 over 2 squared, or 1/4. And so in the negative directions, I'm getting the same values in the denominator, but they were reciprocals of if we had positive powers, okay? All right, now let's try it with let's try it with 1/2 the x power and see what happens. So if I plug in 1, I get 1/2 to the first power, which is very good, 1/2. Okay, so not a big deal. And if I plug in 2, I get 1/2 squared. 1/2 times 1/2 is 1/4. And if you notice, this looks very similar to what we had in the column 2 to the x power. If I plug in 3, I'm going to get 1/2 cubed, which is 1/8. Plug in 4, I get 1/16. Right? If I plug in 0, 1/2 to the 0 power is still 1. And then if I plug in negative powers, so if I plug in -1, I have 1/2 to the -1 power. Remember, -1 power is a reciprocal, so that becomes 2. And so you can imagine then as my x values go in the negative direction, this thing's actually starting to grow. It's starting to double, right? Because I have reciprocals of 1/2 to a power, which would be 2 to a power, right? So these two functions, 2 to the x and 1/2 to the x, are related in that way. They're reciprocals of each other, okay? Now I hope that makes sense. Now, so if you started to graph these things, what kind of stuff happens? Well, let's do just kind of a little sketch, and then we'll jump to Desmos to look at it in more detail. But if I start plotting some of these points, okay, so let's start with 0. If x is 0, I'm at the point 1. So here's 1. If I go to 1, I'm at 2. And here I'm graphing 2 to the x. If I'm at 2, I'm already up at 4. And by the time I'm at 3, I'm off the page. Right? 8 is like way up here. And if I go in the negative direction, at -1, I'm at 1/2. At -2, I'm at 1/4. And as you connect the dots, you're going to get this kind of structure. All right, it's just going to skyrocket like that. Okay, and as I go out to -infinity, it's going to approach 0. Okay, so the graph tells me a couple things. First of all, so 1, exponentials will always be greater than 0. You can never hit 0. Okay, so f of x here is always greater than 0. All right, so in other words, exponentials cannot be 0 or negative. That's what I'm trying to point out there. All right, secondly, for the end behavior, we can think of a few things here for end behavior. On the right, remember, what that means is as x goes infinity, what is this function doing? As x goes out to the positive infinity, this function, it's skyrocketing very fast, right? So f of x also goes infinity. So on the right, we're going up. And on the left, as x approaches negative infinity, f of x actually approaches not negative infinity, it approaches 0. It just goes out to this line. And unfortunately, in our class, we didn't have time to talk about asymptotes. What we call this thing is a horizontal asymptote. Imagine like a plane trying to land on a runway. It never actually lands on the runway, but it always gets a little bit closer. It gets, for each unit over, it gets 1/2 closer. Okay, 1/2 unit closer. Or half the distance, I mean. Alright, so that's the graph of f of x to the 2x power. What about the 1/2 x? So if I was going to graph the 1/2 x, it would do something like this. It crosses at the same asymptote, and it just kind of flips its direction, right? So in the positive way, we're going out to infinity. As x goes to infinity, we're going out to 0. And as x goes to negative infinity, it just skyrockets just like f of x to the 2x power did. So here, this is f of x to the 1/2 x power. Let me try to write that a little nicer. One-half x power. All right, so, and then the purple line is f of x to the 2x power. So for positive bases, when I mean a base greater than 1, we're going to have this thing where the right behavior goes up to infinity. If the base is between 0 and 1, it's going to kind of flip, right? The right behavior is going to go to 0, and the left behavior is going to go out to infinity. Let me show you on Desmos a better picture of this, and we can play around the idea of changing the base to see how the graph's affected, okay? So just give me 1 second. All right, and we are going to graph now. Let's just graph what we just graphed. F of x equals 2 to the x power, and this is on desmos.com. Remember, you can set up a free account. It's very useful. And look, that's pretty much what we did. Okay, but no, look at 7. By the time I get to 7, how far up am I? Well, let's see. Alright, so here's 7. Let's keep going up until we hit the function. Wow, we're really up there. I mean, 2 to the 7th power, oops, 2 to the 7th power is how high? I mean, let's see, 2 to the 4th is 16, so that means 2 to the 5th is 32. Then you have 64, 128. So even at 7, we're already past 100, alright? And now notice in the negative direction, at -1, I'm at 1/2. At -2, I'm at 1/4. -3, I'm at 1/8. And as I keep going farther out this way, I get closer and closer to 0. But if you zoom in enough, you're going to see that I'm not actually at 0. Right? See that? I'm above 0 the whole time. It's just kind of hard to see. Alright. Okay, so there's 2 to the x. Let's try 1/2 to the x power. And see what we get there. And we get a mirror image of what we had. Right? So now let's play a little bit with different bases. So let's see, how about 4 to the x power? What happens? With this green line, which is 4 to the x, it looks like it grew a little faster than 2 to the x, which makes sense because 4 is going to grow faster than 2 to the x. So powers of 4 are going to grow faster than powers of 2. So if I do 3 to the x power, I imagine it's going to be somewhere in between. Yeah, look at that. The purple line's between the green, which is 4 to the x, and the red, which is 2 to the x. And if I did something like this, I keep saying negative, 1/5 to the x power, what do you expect? Yeah, it's going to have a right behavior at 0, a left behavior to infinity, but going out towards a negative infinity, it's going to go up faster than 1/2 x. Okay. I hope this makes sense. And just to give some more, let's see, here's 10 to the x. That's going to go pretty fast. And how about negative, or 1/8? I don't know why I keep wanting to say negative to the x. And we can keep filling it in. So the bigger our base is, the faster it's going to grow. And in between 0 and 1, the bigger our denominator is, the faster this thing's going to grow. Okay. All right. Now what we want to do is, let's play a little bit with the graphs. So we're going to do a couple of examples where we're going to do some graph transformations like we did in the last chapter. And then we're going to look at how do you solve some exponential equations, some equations dealing with exponential functions. So let's try this. This example 2. Let's sketch this graph. F of x equals -3 to the x power plus 1. Okay, now if you remember in chapter 5, we said that we have this transformation idea. So here's the idea. If you had g of x equals a f of x plus h plus k, then what happens is you have basically the same graph, but remember some things change. This stretches or condenses the graph. Or if it's negative, it'll flip it, okay? The h gave me a horizontal shift, a shift to the left or the right. So that was a horizontal shift. And the k gives me a vertical shift. All right, now in the case of exponentials, what does that look like? You would have to have some sort of a, let's say, well, I guess we can change that to, well, yeah, we'll say a, and then you have b to the x plus h power, and then plus k. So your horizontal shift shows up in the exponent. The vertical shift shows out at the beginning. And let me change my example a little bit here. Let's say we had -3 to the x. Let's say -3 to the x minus 2 power. All right, so we're going to apply some things here. So first of all, what is in this situation, if I'm looking at my transformation here, we have -1 times 3 to the x minus 2 plus 1. The negative is not being applied with the exponent, okay? The exponent is around the 3. The negative 1 is being multiplied out front. All right, so here, this is my a value. That's my a value is negative 1. The negative means it's going to do what? Flip upside down. The x minus 2 is a horizontal shift, so I have h is positive 2. And then the 1 is a k value. All right, so then we know that my graph's going to look like this. Let's start off with just a graph of what would be my base. 3 to the x power. 3 to the x power does something like this, crossing at the point 0, 1. And if at 1 you hit 3. Okay, so this is the value 1, 3, like that. Now we're going to take that same graph and we're going to apply our transformation. Okay, so one thing we have to do, the vertical shift says we move everything up 1. So I'm going to move, let me change my color. I'm going to move everything up 1. Okay, so that's my vertical shift. So if I just had that, it would look like this. Same graph, just everything moved up 1. All right. Now I'm going to apply my horizontal shift, which says I have to move everything 2 units to the right. So now where I was at 0, I'm now at 2. So I have to move everything over 2 units, and I'm up here, right? So there's that spot. Let me change my color again. So there's the spot where I was crossing the y-axis. I move that over 2 units. And where I was here, I have to move it over 2 units. And so now this graph would look something like this. It's the same graph as the light blue one. It's just everything's moved over 2 units. Okay, I don't know if that's a little cluttered. All right, and the only thing that's left is now I have to multiply everything by -1, which is going to flip everything upside down. So it's going to look like this finally. I'm just going to mirror image everything. All right, so here you can try, like if, for example, if I plugged in 0 in for g of x, what do I get? -1 times 3 to the -2 power, which would be, so that's -1/9 plus 1, okay? So -1/9 plus 1, which would be 9/9, is at positive 8/9. Yeah, so actually I did this incorrectly. It's going to go like this. I shouldn't flip around I flipped it around the axis. I shouldn't have done that. It's just going to go like that. All right, and you can plug in some test points to make sure you feel good about what you have. But there's your graph. All right, so I went through that kind of quickly. It's not really a big deal. It's not something we worry about a whole lot. But all I'm just showing you is that here's what you need to know. You need to know that exponential functions have this that we call it exponential growth. You may have heard that a lot lately with the spread of the COVID virus, because viruses, at least at the beginning, show up starting out as exponential growth. It just grows like this. Population does that as well. We'll see that in the next section. So all I'm showing you here is that the same function transformations that we learned in chapter 4 apply to this graph as well. The a just flips it upside down. The h just moves it over the 2 units. The k just moves it up 1 unit. And that's it. All right. Now, let's look at something that we deal with more commonly. And this is some exponential equations. And we will only be able to look at a special case of exponential equations, which we call common base. And so here's the idea. Let me show you some examples, and then I think it'll make sense, or hopefully it'll make sense, instead of writing out a bunch of kind of arbitrary steps. So here's my example I'm going to start out with. If I had 2 to the x minus 3 power equals 8. All right, now I can't use my normal algebra techniques. I can't divide both sides by 2, for example. That's not going to help me solve for x. So what do I need? Well, in this case, I can do a clever trick. I can recognize that the 2 with the 8, this is 2 to some power, right? So I can rewrite that as 2 cubed. So now I have 2 to the x minus 3 power is the same thing as 2 cubed. 2 to the x minus 3 power is the same thing as 2 cubed. And so now I have found a common base, we say, right? 2 to this power equals 2 to that power. Now, if 2 to this power equals 2 to that power, what does that mean? That has to mean that this equals that, right? So now what I can do is I can say x minus 3 equals 3. And so once I have found a common base, I'm not dropping the bases, even though we say that sometimes. What I'm doing is just equating the exponents. I'm just setting the two exponents equal to each other because 2 to the x minus 3 power has to equal 2 to the 3 power. So now I can solve this using linear equations to get x equals 6, and that's my solution. And you can test it out if you want. Let's see. 2 to the 6 minus 3 power equals 8. Is that true? Well, 2 to the 6 minus 3 power is 2 cubed, which is 8. It does. It checks. Okay? All right. Now you don't have to check your solutions. I'm just showing you why it works. Okay. All right. So let's look at some examples, and we're going to apply the same technique. What we have to do is we have to get both sides of the equation to be the same base raised to some power. Okay. So this is example 3, and we're going to look at several of these. Let's solve the following. All right. So 1. Or A, we have 25 to the x power minus 125 equals 0. 25 to the x power minus 125 equals 0. Okay. Now, the first thing we need to do is recognize this is exponential. It's got a variable in the exponent. And the way I have to solve this is by getting that exponential by itself. So the first thing I'm going to do here is get the 25 to the x power by itself. So I have 25 to the x power equals 125. Now we need to attempt. So let me write that down first of all. 1, we isolate the variable exponent. Right? We're trying to isolate the variable exponent. Now we need to try to find a common base. Okay, now I don't know powers of 25 too well, but I do know that 25 squared is not 125. So what can we do? Well, what I can do is maybe not think in terms of 25, but remember that 25 itself is 5 squared, right? That's 5 to the power. So I can say that's 5 squared. So I have 5 squared to the x power. And 125, we'll see. What's 5 times 5 is 25. Multiply that by 5, you get 125. 125 is the same thing as 5 cubed. So now, and remember my properties of exponents, I have 5 then to the, if I'm raising an exponent, I have to multiply them. So I have 2x equals 5 cubed. Now that I have a common base, all I have to do is what? Equate the exponents. Once I do that, I have a linear equation. And now we can apply our old techniques to figure that out. I'm going to get x to the 3/2 power. All right, so once I find my common base, we get back to something that we're more familiar with, right? Just linear equations, maybe it's polynomial, right? Okay, I hope that makes sense. Let's try a couple more. So this time I'm going to have we have 8 to the y minus 1 power equals 1/2. All right, let me rewrite that y. It looks kind of like a 4. Y to the 1/2, y minus 1 power equals 1/2. Okay, can I get a common base? That's the idea. We need to figure out a common base. And I remember when I see the 8, what do you think instantly? You think 2 cubed, right? And I think that'll work. Let's see, that's 2 cubed equals the y minus 1. It was isolated already. I skipped that step because it was isolated. Now the 1/2 though, I have to get both sides as the same base. Can you rewrite 1/2 as 2 to some power? Yes. Remember reciprocals. A reciprocal is a negative power, so 1/2 is the same as 2 to the negative 1 power. Alright, now using some properties of exponents, let's clean this up a little bit. That's 2 to the, remember you have to multiply 2 cubed. The 3 gets multiplied by the y minus 1. So when I distribute the 3, I get 3y minus 3 equals 2 to the negative 1. And now I'm allowed to equate my bases. My exponents. Equate my exponents. I get 3y minus 3 equals negative 1. And this is a linear equation. So I get 3y equals adding the 3 over. So negative 1 plus 3 gives you 2. I get y to the 2/3 power. And there's my solution. Hope that makes sense. The hard part is finding the common base. If you can find the common base, the rest of it kind of just falls into place. Let's try another one. Ooh, this one's going to be a little bit tricky. 2/3 the x power equals 9/4. Okay, so we have fractions. And I'm not too familiar with my fractions, but the easy thing is about fractions raised to powers is you can just think of the numerators and the denominators separately. So what I mean by that is 2/3 cubed, for example. If I had 2/3 cubed, that's the same thing as 2 cubed over 3 cubed. So I don't even have to know powers of 2/3. I just need to know powers of 2 and 3. Alright, and I think 2/3 is my common base here because 2 and 3 are both prime. And so that kind of gives me a hint that I can't really do anything with them. So I have 2/3 the x power. Oh, and I recognize here that 9 is 3 squared and 4 is 2 squared. Okay, so that would be the same thing as 3/2 squared, which is not the base I need. I need 2/3. So maybe we went down the wrong path, or maybe we need to remember, again, reciprocals. I can say 2/3 the x power then is the same thing as 2/3, right? I took the reciprocal of 3/2, and so what do? You make the exponent negative to the negative 2 power, and therefore I get x equals negative 2, and there's my answer. Make sense? I hope it does. Okay, equating common bases is the best, or the first strategy we apply to exponential equations. Sometimes you can't do that, and so if you can't do that, you need something called a logarithm. Now, I wish we had time in our class to cover logarithms. It's very, very useful. Unfortunately, we're out of time, but equating bases is still a very helpful technique. Exponential equations show up in a lot of places. So in the next section in 7.2, we're going to look at some examples where exponentials show up. If you take a class called differential equations one day, the majority of your solutions in a first semester differential equation course are exponential equations. So these things show up a lot, or exponential functions, I mean. Guys, if you have any questions, let me know. I appreciate you hanging out with me this semester. Hope you learned something. Hope you do well going forward. Just let me know how I can help you. I hope you have a great week, and we'll see you later. Take care.